Yes. So let me spend some time on the homework last time. So in general, almost all the correct solutions have been provided by both teams. And of course, you work hard till midnight. That was, of course, is not the intention. The intention was that every team can work closely and can discuss between the students and complete the homework together. So in general, the submissions are quite okay. It's only for one missing point. I will discuss in the problem number 3. I think number 4 or number 3. Oh no, number 5. Number four, probably. We will spend more time on that problem because both teams make minor mistakes there. So the first one is quite straightforward because the key to this question is that once the DF is also the bisector of the angle BDA, because here we have a right angle and the O F on BDC, where is a angle 180. So basically, if DE is a bisector of CDA, and the DF will be the bisector of the BDA. And then, of course, you can use the angle bisector theorem, get a pair of the proportions of CD, AD, is the same as CE and EA. So we use DA as a bridge. We use DA as a bridge to link the two, let's say, proportional relations from the both angle bisectors. So DA is a bridge. So then basically you have the CD, DA, CE, EA, and DB, DA, BF, and AF. So DA is the bridge. So basically you have 5 sides already. So no, 6 sides. So 3 sides from one bisector. So basically that's all the 6 sides or 6 segments we needed for the Sever's theorem. So this one is easy. Second one, we have to make use of the G, which is the central. And I see many of you make an auxiliary line like AG, and it's also the same as the CG. But what I did is was using the CG instead of AG, but AG can also work. So make use of central G, and also the Menelaus theorem, where the EF is clearly transversal of the triangle. Of course, you have to see which triangle, and instead of use ABC directly, here we can use the two, let's say, small triangles like ACH and the BCH. So we apply the Menelaus theorem in both ACH and the BCH. So where again the CG and the CH is used because here we know the proportion is a 2/1 because G is a central. Yeah. So here actually it end up like the proportion of AH and the BH and the BF. So that's something we have to elaborate a little bit on these correlations. You can also make a line like AG and then H is here. So that's exactly the same. You can discuss, okay, what's the DH, what's the BH, and the CH, because H is the middle point of BC. So that's very similar or exactly the same. Okay, number 3, now we are discussion the, let's say, Seva or Menelaus theorem within a circle, And of course, here instead of only let's say a 3 points or a triangle, here we have a 6 points or a hexagon in such an order, the A, B, C, and D, E, F. And we have to show these three diagonals are concurrent if this relationship exists. So what I did is try to show how can we convert the, let's say, the proportional relationship of the segments into let's say, the relationship of the sine function. So now we use a trigonomic, we call it trigonometric Sever's theorem, where we use a sine function of each angle instead of the segment, right? And here, of course, we have the, let's say, we have the condition like the segments. So basically, each segment can be converted into the angles. I make two additional lines here, and the BG, for instance, is the diameter, and the GD, of course, as another, let's say, another chord. But you see the BD M converted, the BG is the diagonal as a 2R. Now it should be small r, but I use the upper R. And with the sine function of these angles, BGD, right? BGD. So it's the 2R times the sines BGD, but the BGD basically is the same as the BAD. So it's the same angle as this one because of the same inscribed angles. So basically the BD can be converted into a constant, whereas the diameter of the circle times sine function of one angle here. So now you see, okay, this is one segment, and for the other segment, it can all be converted into the sine function of each of the 6 angles. And immediately we have the trigonometric Sever's theorem. So that's very straightforward as well. Okay. Number four is a little bit more challenging. As I said, the both team made a minor mistake here, or missing part, and also mistake, but missed one discussion. It's a good idea that you say, okay, I extend EF and CD to meet somewhere else. Another point like UVW or XYZ, whatever you call it. But you still need to discuss the the scenario where the CD and EF are parallel to each other. Because it's not given in the figure here that the CD and the EF definitely will intersect each other. So that is the weak point of your proof. Yeah? So you lose 2 points from each team. What I use here is a little bit more complicated. I would say it's not straightforward, but it is a proof. Maybe it's not the best proof. So where I used actually also use the sines. So use a lot of cases of science law in the triangles. But basically it's end up like it starts with like the proportional correlation of this function. I mean, if you have any intersection code like B, C, and the EF, you always have such correlation because it's just use the law of the intersection codes, or to use the law of the sines in the different triangles. And using this and this, and similarly in this, and then you can end up with the proportional, the values of the sine function. But here, I mean, in the discussion of in these small triangles, I mean, the XDR and XDF, the proof here is not so straightforward. I think there should be a better proof, but what I used a lot of like similarity of the triangles and also the inscribed angles, and also the science law. So it's not so straightforward, but good enough is that we can find the solution, we can find the proof as desired. So I do think there will be a better proof for this question. Number 5, I think that's quite interesting to use the analytical geometry. I think both teams use analytical geometry, and Yuchen's team use the factors, and the Lucy's team use analytical. I mean, to set two-dimensional coordinate systems. So that's very interesting. Yeah. So I do encourage you and to learn how to use, for instance, the vectors, to use the, let's say, the coordinate systems, or to use a complex system, a complex number system to solve the geometry questions, because it's straightforward. Of course, sometimes you need more calculations, especially for the complex number system, but that is the easy way to solve some geometry system, especially here, the fixed proportion like AE and CE. You can easily use the vector of the E, which is like 3 times A plus 1 times C divided by 4. And it's very straightforward to find, okay, the PQ, the, say, coordinates of PQ, for instance, and build up a linear function of Mn, and to fit the P and the Q in this function. If we're talking about the traditional geometric solution, we can also use the Menelaus theorem or the Sebas theorem here. So basically, I also built the Mn first, and to try to prove that let's say the S, to let the S and R are the MM intersecting with the AC and the BD, and try to prove that SQN are collinear and RPM are collinear. By this way, you can show that PQ are on the same line as MN. Yeah. So I'm going to skip this proof here. So basically, you can see we can prove we can divide this question into 2 parts, the upper part and the lower part. So in each part, we can show that, we can show the SM, for instance, is transversal of the triangle OAB and end up with OEF, because P is the midpoint. So then we immediately have the EP over PF is 1. So then we can use the Menelaus theorem to show that S, R, P are collinear, because S, R, M are collinear, meaning that P, M, S, R, the 4 points are collinear. And by the same way, we can prove the upper part. So that is the main idea, to use the Menelaus theorem here, because all the segments, we know better what is the proportion, what is segment proportion. So it's very easy to think about using of Seva or Menelaus theorems. Okay, and last one, it seems like an IMO shortlist question, but of course it's an easy one. I really like the solution from Xiaoshito's team, where you show basically the quadrilateral. I mean, all the 3 triangles are similar, so that's trivial to find. And you can just combine the 2, let's say, neighboring triangles as quadrilateral, and actually the 2 quadrilaterals are also similar. So you find the corresponding points in the 2 systems, and you can always apply let's say the relationship of the proportional segments. And that's also smart solution, smart proof from Shashito's team. And we can find also, we can use a more traditional way. We can find, okay, basically the AX is also bisector of the BASD, and the AY is also bisector of angle CAE, and then we can use similar proportional relationship. And a small trick here is that when you have such pair of the proportional relations, and you can always say, okay, AX/AY is AB over AC, and AC over AD. You can always make a subtraction here, saying the same proportion, but use the numerator, the difference of numerator divided by the difference of the denominator. They'll also be the same. So that's why we can immediately AC over AC minus AX, because AC is a long segment, AX is part of this segment, so we can say the CX and the DF. Also introduce CX and YD, okay, or another way around, the XC and the YD into the game. Yeah, so then by this you can see already, oh, this is part, this part, this part is part. So for the Seva serum, we have 1, 2, 3, 4, and the other two segments that's actually to show the equivalency, not the equivalency, the equality of these two segments, showing the Q bisector CD. Yeah, so that's very interesting proof. Okay, so that's the end of the homework. Let's switch to the mock test. Mock test, I got like five submission from all of you. I think it's always good. I don't think Xiaoshito also did the mock test for the VWO, but actually it's the same. VWO and YWO, we basically part of the questions are the same as the tradition, as the same as the real VWO or YWO. They also have part of the questions overlapped, but for the VWO set, we have more on the, let's say, trigonometric functions, also function shapes. There's also the difference between the VWO and YWO. I don't know exactly in OMB, the OMI, Maxi and the MIDI, there must be also some differences, but Yushen also did this mock test and the results are good. Okay, so we start like the most, not the most difficult, I would say the question with the least correct rate. We have a 5 submission, but unfortunately, none of you have solved it. Maybe it's just due to some silly mistakes made in the calculations. Let's go through the question. So actually, there's a convex angle, and the condition said all the internal angles have integer degree values less than 180, of course, because it's convex, and they are different. So basically, there are different integers. And what is the largest possible value of n? And to answer this question, of course, we have to maximize the number of the sides, right? The number of n, the value of n, meaning that we have to minimize, the integers and the internal integers. If we have the smallest integers, and then of course we can have more n's. So basically, we can conclude there are 3 conditions. So instead of the internal angles, we focus on the exterior angles or external angles. Why? Because if we talk about the internal angles, and the sum of the internal angles is a function of n, right? It's like n minus 2 bracket times 180. Yeah. If we're talking about the exterior angles, the sum of exterior angles will be always 360. So it's an easy case for us to evaluate the ends, right? So basically, the internal angles are different integers. Of course, that's the same, and that means the exterior angles are also different. They're also integers because the 180 minus, right? There's 180 minus the interior interior angles. So we have three conditions. One, they are all integers. Second, they're all different. Third, the sum is 60. Yeah, and we have to also maximize n. So we add them up. Like say, if we want to max n, and then we have to decrease. We have to minimize the exterior angles. Let's say the smallest possible interior angles is 1, of course, integer. Yeah, and the second should be different integer, so should be 2 and 3 and plus n. So say if we have n sides and the n exterior angles, and the sum up should be no larger than 360. So we get easily inequalities like this. Yeah, and we found the two roots. One is a negative value, and another one is equal to n is no bigger than square root of 881 minus 1 divided 2 is like 26 point blah 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 plus 3. So the largest possible value is 26. Of course, you say 1 plus 2 plus 3 plus 26 will still have something remaining, but we add the remaining to n. So that's done already, right? Like 1, 2, 3 till 25, and the last one is not 26, but like 28 or 29. I don't care, but the number of these sides is 26. Yeah. So that is the answer for this question. The second one is also strange for me. Only one of you got the right answer. So what is that? So in this question, you see 4 circles, yeah, like a big circle and the 2 circles and the small circles. All circles are tangent to each other. So to solve these questions, there's also tangents, not only for the tangency between the circles. Sometimes you have tangency of the circle with a triangle, with a square or rectangle, for instance. In this case, the first side is always like connecting the center of the circles and connecting the tangent points of the centers at the centers of the circles. It's always good. If we make these auxiliary lines. And in this case, what I connect here is the P, basically the PQ, are the centers of the medium size and the smaller size circles, and O is the center of the big size circle. And you see immediately we have a triangle, and out of the symmetry is a right triangle, right? Right triangle, and the O has an angle of 90 degrees. And the rest part work is to find what is size, what is the length of the segment. And PO, of course, PO is the radius of the medium size circle. And QO is the difference between the radius of the largest angle, largest circle, and the smallest circle, because of the R, the big circle, minus the R, the small circle. Yeah, so that's very easy. The OP is 3 because we know that the medium size is 3. Yeah, and of course that's the OP and the OQ and the Q and the PQ. So that's easy. Yeah, it's very easy to have a Pythagorean triangles, or Pythagorean relations, and solve the axis too at the end. So that's should be very straightforward. But if you see similar questions in the EVO or VWO competitions, if you see a lot of circles tangent to each other and tangent to a square or rectangle, for instance, the first instance to see is the connected center of the circles, connected tangential points in the circles, and most times they have some like collinear or forming some triangles. Okay. Then, okay, I got the chat. Let's see. Yeah, yeah. So that's the final MIDI. So the questions comes from, of course, the questions come from the 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 real questions, the OMB and also the VWO, VWO, and other competitions. Yeah. So here you have all the references. You can find all the references. The last one is from, of course, a Swiss Mathematical Olympia. Maybe that have the same question in the OMB as well. So number 3, but actually is a Q17 from OMB MIDI semifinal. You see again, there's a tendency here. So you have a point C which draw two tangent lines against the circle A, and we know that the TCT prime is 60 degree, 60 degree. But basically, out of the symmetric, actually you can find the TCA is 30 degree, and here you got a right angle. So always say connecting the center and the tangent points. Yeah. So here you get a 90 degree, and this very easy to find. Okay, if this is the radius, and this should be 2 times the radius, and CT should be square root of 3 times the radius. Yeah. So then you get all the, let's say, relationship with the segment. What is asking? Let's say, what is the area of the surface bounded by, yeah, these two half lines and the small arc of T prime. So this is asking what is the area of this part, and you see that should be 2 times of the triangles subtracting a sector, right? The sector, you know, here is the 30 degree and here is 60 degree. You have 120. 120 is actually 1/3 of the circle. So that is very easy. The 1/3 is pi divided by 3 because the radius will be 1, right? Radius is 1. Yeah. So that's also straightforward to find the solution. Again, I don't think only 2 of you know how to solve this question, but sometimes, especially in the multiple choice questions, there's some traps. So just aiming to aiming for any silly mistakes you made. Yeah. So in the calculations, be careful. Sometimes you know how to solve it, but just due to the mistakes made in the calculations, you get a missing point. Let's say instead of the right answer, you get another answer. Yeah. Pay attention to these silly mistakes. The next question from SMC again. So 2 of you found the right answer. How many solutions there are equations like 1 plus 2 times sine x, yeah, minus 4 times sine square x, minus 8 times sine cube x. So if I saw this question the first slide, I would say, oh, indeed, that's combination of the sine function and a polynomial function. It seems quite complicated. But I see the second side is that, okay, I have the 2 times sine x and 4 times square and 8 times cube. So basically the coefficients is also in the same powers, right? The sine's power and the power of 2. They are the same power, the same exponent. So that's why I give them a hint. I can just replace the 2 sine x with y, for instance. Yeah. And then, of course, the second term becomes 1 plus y, and 4 times sine square x is like the y square, because this is 2 square of 2. So the y square minus the cube of y cube, yeah, because 8 is cube of 2. So basically, we have simplified these equations into a pure polynomial equations. And you immediately see here it's 1 plus y. Here you get both minus. So basically, they both have the factorial factor of y squared. So you still have 1 plus y. So you can easily factorize this like 1 plus y times 1 minus square of y, and by difference of power, difference of squares, you can have the finally this the final factorial. The y have actually three roots, and the two roots are kind of overlapping or the same roots. So y is minus 1, and another one is y is 1, and replace it back with sine x. So with sine x is minus half, or sine x is half, and you see, okay, in the period of 0 to 1 to 360, or 0 to 2 pi, there were four solutions, of course, yeah. For each of them have two solutions. Yeah, if we draw, I'm switch to my pen. So basically, you have the sine function like this. This is a sine function, right? So you have the 0, and it's 360. So you get a half. So this is a half. This is a minus a half. So here, you draw a line, and you find four solutions. So 1, 2, 3, and 4. So four solutions. Okay. Next one, very similar to one of these examples in the Seva or Menelaus theorems, right? But this one is easier. It should be easier. You don't need to learn to use Menelaus theorem here. This basically is talking about the areas, yeah? And if we know the ABC and the DEF are the dividing each segment into 2/1, and we know the triangle ABC has the area of 702. What is the area of DEF? DEF. So my thinking is that, okay, if I know the proportion of ADC, for instance, this one, ADC over the ABC, and then I can have the final answer by subtracting the three small triangles out of ABC, right? Yeah. And the only lag is that, okay, I have to connect AF, BD, and CE. Yeah. So let's let the DEF as X. So I don't know what the X is. And the EF, because EF is double of BE, right? So the DBE should be half X, of course. Yeah. DBE should be half X. And then because AD is half of DE. So then ABE is half of the DBE, then it should be the 1/4 of X. So then you know all the parts. So 1/4, half, 1/4, half, 1/4, half. So you can add them up, yeah, and then divide by the 700, divide 700 out. Sure. So basically, then you easily find the ABC is X plus 3 times of half X, 3 times 1/3 of X. Yeah. So then we can calculate back X is like 216. I don't know what happened in your calculations, but I do think this question is not so challenging. Maybe just due to the silly mistakes made. Yeah. Okay. Now this one here, I had this question also in the EAVO mock test, but the same. Many mistakes are made. I have a very low correct rate, but I don't know what is the problem here because it's quite straightforward. Maybe you just missed an addition like BD should be an integer. BD should be integer. Yeah. So some of you just select E is like an infinite number or infinite many, but I don't think so because it's the BC, CD, AD, AB are fixed. So basically the quadrilateral are fixed in the range, in a small range. So BD cannot be infinite large, BD cannot be like 100 or 200. Why? Yeah, why some students choose E? I don't understand why. Yeah. So what we going to use? It's very simple. We use inequality of the triangles. Yeah, like the B, I say at ABD, look say ABD here. So ABD we have two sides, and BD is the third side. And we know always that one side in the triangle is no larger than the sum of the other two sides, and no smaller than the difference of the other two sides. So that's very fundamental inequalities if we're talking about triangles. Okay, got the chart again. Okay, so Joanne said I forgot the second triangle equalities. Okay, so you use the first triangles, and then what the sum of the two sides is basically is 15, and the difference is 7, right? So we got the first inequalities, and we use the same as the CBD, and of course the values are different. Okay, 小石头 don't see the integers, yeah, the real number is. Okay, so basically from the second one, you have also a inequality, of course, with different numbers. And then you combine these two inequalities, apply the stricter or stricter conditions, of course. There's there's no less than 7 instead, and here is no bigger than 12. So from 7 to 12, we get 6 possibilities. Okay. Now get again this one. So we get 3 of you get the right answer, and again some tangent contact. Some tangent. Q is the tangent point of the 3 different circles, and P is the tangent of the smaller circle with a line here. So it's asking what the statement and what is the relations between these areas. Whose so what I'm doing now, always to connect, for instance, the centers of the circles, right? Center of circles. The center of the small circle, the white one is here, and let O be the center of the bigger circle, and the yellow one. And we can have again the triangle. You see again a triangle, right triangle appears. And what is the side length of these segments? The OR, of course, the largest radius. OP is larger radius minus the diameter of the small angle. Yeah, and then you get this already, right? And of course you say, oh, what about the blue one? The blue one, of course, the radius, the OP, the radius is the blue one's radius, right? So the diameter of the white circle is the radius of the blue circle. So we have all the relations already. Yeah. So for the rest, it's easy. For the rest, easy. So you know the correlation of the large circle, the OR, is twice of OP, and OR is R. The OP is R minus two times the radius of the white one. So it's easy to find the correlations, and we find, well, what is the relations of this AF, G, and H. So that's also very easy to have. Okay, this one is also interesting and also easy to make mistake. I think maybe how many of you select, for instance, how many of you select like 48? I don't know how many of you select 48, but basically you see that's 24 hours period, but the two hands will meet again at noon at 12 o'clock. So we can divide this 1 day period into 2 congruent periods. I mean, from 0 to 12 and times 2. Yeah. So from 0 to 12, basically in each hour, there are two time slots where the two hands are perpendicular to each other, right? So that's quite easy, but just pay attention there's a 3 o'clock and 9 o'clock. Yeah, the 3 o'clock itself, where the hour hands and let's say the minute hands are already perpendicular to each other. So basically, these slots are counted in 2 hours, in 1 hour before and 1 hour after. Yeah. So that's why we have to subtract 2 time slots. So we have like 3 o'clock and 9 o'clock. Yeah. Or each hour have 1 overlay. So we have to subtract 2 times. Instead of 24 for half day, we have only 22 for half day. And for the whole day, we have 44. Yeah. Okay. And then this one, that's very interesting because I do think we have a similar examples from OMB where it's asking to find the, let's say, the parameter of like the inner part. Now we're asking for the outer part. So if we connect all the centers of the circles, again, connecting of the centers of the circles, and you find a regular hexagon, right? And you see each angle, each exterior angle is like 360 minus 120. Yeah. So the length of the curve, the length of the arc is like 2/3 of the perimeter of one circle. Yeah, it's 2/3. Yeah, because it's one, this is 120, this is 240. So each part is 2/3 of the whole perimeter, and then you have 6 parts. So basically have the 4 times of the surface. Now, of course, the surface, because it's like a cylinder, right? Cylinder, but basically you can cut on the length of the arc and also the perimeter, 4 times the perimeter of one circle. So it's 4 times. Okay. This one is kind of a logic question. That's also very interesting. I think we explained it before, like 2 years ago or 1 year ago, I don't know, where we use also the number 9 or number x, because you see there are five inhabitants. Say, okay, the first set of my number is strictly greater than 1. So you say, okay, starting from 1 to here, and strictly, meaning that you cannot be 1. So I make a hollow point, not including 1, but strictly it's much bigger. It should be bigger than 1. And second set, my number is strictly greater than 2, and then also 2, 3, 4, 5, yeah, and so on. And in another order, each of them make a second statement. My number is strictly less than 1, less than 2, less than 3, and less than 5. What is the larger possible number of elf in this group? Mean that, okay, I should find the max regions, the max number of the regions where at least they are coincide with the statements, right? And say, okay, here basically you cannot find this one because it can not all the 5 ones are correct, right? Because then you have a contradiction. Yeah? You don't have any. If I draw a line here, for instance, if we draw a line here, and you only have a statement from the red ones, not from the brown ones, because you shoot the elf who tells the truth, always tells truth. So you have to find a pair of the red region and the brown region, and that means that should be one elf, right? Who tells always the truth. So basically, you can find like 2, 3, and 4 because they are all, let's say, integers. Everyone have integers. So then you have only 2, 3, and 4, where both lines, you have the red lines and all the brown lines here. But you cannot have this one. Why? Because strictly bigger. Yeah, so meaning that the ground ones should be somewhere here, not exactly passing this number. So the number 1 or the 5 is not applicable because it has only one line, not the both lines, because actually this line also not applied strictly smaller, strictly larger. So that's only the 2, 3, and 4 are possible. So only 3 possible elves. Okay, then again, this question, let's see how it looks like. Number 1 is written on the blackboard and change the number step by step, either multiply it by 3 or subtract 1. What the minimum number of the steps need to reach the number 2023? So we have another way of thinking. It's kind of adverse thinking from the end to the beginning. Yeah, the end is 2023, but of course it cannot be obtained by multiplication of 3. Yeah, so must be a result of subtraction. So before this one should be 2024, and before that 2025, and even the 2025 is a multiple of 3. So that's why the only possibility is that from 2023 back towards 2025, and then we can use the multiplication. Of course, we're aiming to have the minimum number, so that's why we have to apply multiplications as many as possible, So then we divide 2025 back to 25, because you have like a 4 factor of 3. And then 25 again is no multiple of 3. We have to add up again to 27. 27, fortunately, is like fourth power of 3. Yeah, so from 1, 3, 9, 27. So we count all the steps. So in total, there are 11 steps. So that's why 11 steps is the minimum number of the possible steps. Okay, then this one, how many square numbers are here in these sequences? So that's basically the n to the n, right? And to think about the square numbers, there are 2 cases. One is that if the base itself is a perfect square, and of course, no matter what the exponent is, it's always be a square, right? Second case is that no matter what the base is, if the exponent is even number, and then this power will be a square. Yeah, but do not forget the exclusion and inclusion theorem. Yeah, you have the 2 scenarios, but you have the both. Yeah, you have the both, meaning that okay, the base itself is a square, but the power is also even. You have to subtract that once. Yeah, so you can do the both. Yeah, so consider the 2 cases and then subtract the ones in the middle. So use the exclusion and the inclusion theorems. But then, of course, you can also consider the odd and even numbers. Here, I use this approach. I discuss only among the odd numbers, meaning that, okay, there's no case that the power, the exponent is always odd. So we also talk about the odd squares. Then we have like 40, yeah, 45, for instance, 44 instead. And then we can also discuss the even numbers, even numbers. So basically, at the end, you get like 1034. But 3 of you get the right answer. Yeah, that's also good. And this one, some sketch of the function shapes. And you might think it's quite challenging because here you have inverse function. I don't know, maybe some of you have not learned inverse function. Yeah, so it's -1 stands for the inverse function, but I would say function itself, no matter it's inverse function or whatever, here is like -1, and you have like it should be a even function because cosine is an even function. You have a -1, so it's a reciprocal. I think it's a reciprocal, this one. And then you still, it should be still in the form, in some form of cosine. So the sine, like cosine x, something like that. X, yeah. So we know the cosine x is even function. What is even function? Even function means that you always have a symmetric over the y-axis. The cosine, you know, is something like this. Yeah. So it's symmetric over the y-axis. And this function is a combination function of cosine x. And it stands for cosine x. So actually for the even functions, like fx is always same as f minus x. So that's for the even functions. So if you plug in the minus x in, so you get also fx is f minus x because cosine is even function. So then you judge on the five shapes, which shapes are symmetric over the y-axis. And this one, of course, not. This one is odd function because it's symmetric over the origin point. And this one is the one symmetric over y. This one is the odd function, which is symmetric over the point here. This one also odd function. So only C is possible. I do not check some special point here, but I see only C has an even function. So that's why C should be the right answer. Okay, so that's all. That is all. And I think basically you did a very good job. And of course, now it's the ending of this semester. We won't have any follow-up. Yes, it's a reciprocal of cosine. Sorry, it's not the inverse. Okay. And we do have, let's stop the recording. Okay. We do have a parent contact scheduled. So if you want to have some additional discussion with me or your parents with me, you can still make a reservation by today. The link, you can follow the Doodle link sent by 4th of December. And then, of course, for the coming EVO, VBO first runs, which will be somewhere middle of January, I think OMB had the same dates. So you should also set aside some time during the Christmas holidays, prepare for the first run. But I don't think the first run will be so challenging. Yeah, but do have some preparations, especially for the second round. You will have some time pressure for EVO or VBO because it's reduced from 3 hours to 2 hours for the second round, and it's much more challenging. But you also have all the slide deck from the group OJ this semester. So if you have time, just go through the slide deck of OJ because they focus on the first 2 rounds. Yeah, it's really interesting and also could be some help for you to prepare for the first 2 rounds. I do think what we learned this semester and also the year before will help you a lot for the finals, but we have to do it step by step. So meaning that passing through the first 2 rounds is critical. Yeah, you have to make sure you are qualified for the final before we can say, okay, you have a large chance of success in the finals.